Okay, in this video we're going to be looking at the gravitational force worksheet. And quick reminder, when we're talking about the force due to gravity, in most cases before we talked about the force due to gravity being the mass times the acceleration due to gravity. But in this situation we're going to look at the case when we don't know the acceleration due to gravity. We're going to look at Newton's universal law of gravitation, in which case then the force of gravity becomes that it's the gravitational constant times the product of the two masses. So the force of gravity is dependent on the two masses, and that it's inversely proportional to the square of the distance between them. Now this big G, this constant, is called the universal gravitational constant, and it is equal to 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. Okay, and you can find this on the front page of your reference table. We got to make sure that our masses are in kilograms. We got to make sure our distances are in meters. Okay, so if we look at the first one, Oscar, whose mass is 65 kilograms, so we know mass 1 is 65 kilograms. And Olivia, whose mass is 45 kilograms, so we know mass 2 is 45 kilograms, set 2 meters apart. So the distance between them is going to be 2 meters apart. Force of gravitational attraction, so we're going to use F sub G is equal to big G, M1, M2 all over R squared. So 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared times my two masses, so 65 kilograms times 45 kilograms. And we're going to divide that by the distance between them. Don't forget the square. And when you do that, you're going to get, I got to jump over my answer key, 4.88 times 10 to the negative 8th newtons. So the force of attraction between them is not huge, which you would expect. Relatively small masses, only 2 meters apart, you'd be expected to be relatively small. Now, on the next one, we're going to look at things that have extremely or much larger mass. So now, force of gravitational attraction between 1.8 times 10 to the 8th kilograms. So mass 1 equals to mass 2, which is equal to 1.8 times 10 to the 8th kilograms. Worn apart, so their centers are located 94 meters apart. So R is equal to 94 meters. And again, we're looking for the force due to gravity. Forgot to put that up here. So going to use the same equation. F sub G is equal to big G, M1, M2, all over R squared. So the 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. I know this gets to be a pain in the butt writing, but it's important to put it in there. Times the two masses, so 1.8 times 10 to the 8th kilograms. And since it's M1 times M2, I'm just going to square this since they're both the same. And then I'm going to divide that by the distance between them. Don't forget to square it. And when I get this one, I'm going to get 244.6 newtons. So a little bit bigger. Again, that mass is much, much bigger than what we had before, so much, much larger force. So the next one, we have the force of attraction between two masses. M1 is 1.3 times 10 to the negative 4th kilograms. And mass 2 is 2.4 times 10 to the negative 3rd kilograms, and they give us the force of attraction, or gravity, so 2.65 times 10 to the negative 6 newtons. You're looking for the separation, so you're looking for R. So in this case, same equation. F sub G is equal to big G, M1, M2, all over R squared. And you'll notice that a lot of these have exponents, so if you have difficulty putting these times 10, the scientific notation, into your calculator, come see me, so we'll talk about it and get it cleaned up. So this is going to be 2.65 times 10 to the negative 6th newtons is equal to 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. We're going to multiply that by the first mass of 1.3 times 10 to the negative 4th kilograms. And the second mass, 2.4 times 10 to the negative 3rd kilograms, all over R squared. And so we're going to cross multiply that, and you're going to end up with that R squared is equal to all of this on the top divided by that force of gravity, and then you've got to take the square root. So your R comes out to be 2.8 times 10 to the negative 6th meters. Now, next one, Mr. Paget, whose mass is 100 kilograms. So M1 is 100 kilograms. It's a demo for their classroom. How much gravitational force is exerted on a 55 kilogram student in there? So M2 is 55 kilograms. And the distance away is 1.5 meters. And then we're going to have a third one, so M3 is 65 kilograms. And R, my new R, so I'll make this R2, is 4 meters. And you don't have to rate it as R2, but I need to know that it's a different set. So I'm going to run this twice. So my force due to gravity, big G, M1, M2, all over R squared. And so that's 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared, times my mass, that 100 kilograms, times the 55 kilogram, sorry, 55 kilogram, I wrote that wrong. That should be 55. Let me change that out so I don't screw it up before. 55 kilograms. And I'm going to divide that by the distance, which is 1.5 meters, but don't forget to square it. And that's going to give me a force of 1.63 times 10 to the negative 7th. Now my force of gravity for the second one, again, big G, M1, M2, or second situation I should say, times R2 squared. So again, the 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared, times 100 kilograms, because my mass doesn't change, times the 65 kilograms. So we've got an increased mass. So you would expect it to be a bigger force, but we've got a further distance away. It's 4 meters. Don't forget to square it. And so when we solve that, we get 2.71 times 10 to the negative 8th. So even though this boy had a larger mass, because of his increase in distance, the force of gravity is actually going to be less. Continuing forward, what distance separates? So we're looking for R, question mark, a mass 1 of 100 kilograms times mass 2, which is 40 kilograms. And we know the force due to gravity between them is 2.95 times 10 to the negative 9th newtons. So force due to gravity is equal to big G, M1, M2, all over R squared. So you know the force, which is 2.95 times 10 to the negative 9th newtons. 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared, times M1, which is 100 kilograms, times the 40 kilograms, the mass of area, kilograms, divided by my R squared. So again, we cross multiply, and when you find that out, R is going to come out to be 9.51 meters. Okay. Number 6, the force between two identical basketballs. Okay, so we know M1 is equal to M2, and we know the force of gravity is 2. This is a typo. This should be newtons. My fault. So I'll have to go back and change that. So 2.8 times 10 to the negative 11th newtons, and we have a distance is 1 meter. Now, M1 and M2, that's my unknown. So I'm going to use my force due to gravity here. Big G, M1, M2, all over R squared. But before I put in numbers, I just want to talk about this really briefly. Since M1 is equal to M2, I could rewrite this equation to big G times M squared, because M1 times M2, since they're the same, at least those two things squared, over R squared. So now I put this in, so I've got 2.8 times 10 to the negative 11th newtons is equal to 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared, times M squared, all over 1 meter. Don't forget to square it. So we cross multiply that, you're going to get 2.8 times 10 to the negative 11 times 1 squared divided by the 6.67, and so then that's going to equal M squared. So then if I take the square root of that, I'm going to get 0.65 kilograms. All right, 2 more. We've got, what is the gravitational force of attraction between Earth and Sun? Is 1.6 times 10 to the 23rd newtons. What force would this be if the Earth would have been twice as massive? So for this one actually we don't get a lot of we don't get any numbers other than what the force is. But I know that force due to gravity is equal to big G times M1 times M2 all over R squared. So if they don't give you a lot of numbers, but they're asking you how much it's going to change, it's actually easier just to make up numbers. And so what I'm going to do is I'm going to say, just say that big G is 1, M1 is 1, M2 is 1, and R is 1. Don't forget to square it. That'll give us a force of 1. Now, if I keep everything the same except for M2, so this is my change, big G is 1, M1 is 1, but now M2 is going to be 2 times as much divided by 1 squared because the distance doesn't change. This would now give us a value of 2. So if it was 1.6 times 10 to the 23rd, now if I double the mass of the Earth, it's going to be 2 times as much. And so that'll give us a force, a new force, so 2 times the 1.6 times 10 to the 23rd newtons. So that's going to be 3.2 times 10 to the 23rd newtons as our new force. And the last one now, the gravitational force, so it's very similar. Force of attraction between the Earth and Sun is this. Will the force be formed twice as far away? So we're going to use the exact same thing. We're actually going to use this part again. So had that stayed the same, but now we're going to keep big G the same, M1 the same, M2 the same, but now we're going to double that distance. So my distance is going to be 2. Don't forget to square it. When I get that now it's going to be 1/4. So if it was 1.6 times 10 to the 23rd, now it's going to be 1/4 as much. So my F2, I guess F3 maybe, whatever this one, so force we would get here, is going to be 1.6 times 10 to the 23rd newtons divided by 4. And so my new force is going to be 4 times 10 to the 22nd newtons. So these last two are a little bit tricky, but I think with a little bit of practice, you're going to be fine with them. So come see me if you have questions, and hope you ever have a great day. See you later, bye.